Okay, so finally let's go back and look at what we've learned from the Bell inequalities about the issue we started with, which was local realism, and Einstein's belief that nature must, that we must be able to look inside and see the gears and the wheels behind the scenes that nature must be using to keep track of things. Okay, so let's look at our CHSH game. Alice and Bob got as inputs bits X and Y. The output bits A and B. And the condition that they must satisfy is if X equal to Y equal to 1, then A is not equal to B, else A is equal to B. So now let's go through and understand exactly why this cannot be satisfied in any sort of classical-like scenario. Let's make up a table. Here's X, Y, A, and B. Let's say that the input was X equal to 0, Y equal to 0. And we want to know what could Alice and Bob possibly, what should Alice and Bob output in this case. So first thing we can say is, without loss of generality, we may as well assume that Alice outputs 0. Because if she were to output 1 in some successful strategy, we could just flip all of both Alice and Bob's answers in all possible cases. And then, since all we want is whether Alice and Bob output the same or different answers, we won't change their success probability in any way. So we may as well assume in this case Alice outputs a 0 without loss of generality. So now here's a crucial observation. If Alice and Bob wish to beat the 3/4 mark, then they have to be correct. They cannot afford to make an error in any of the 4 input scenarios. So in order to be correct, Alice and Bob must have matching answers, so Bob is forced to answer 0 in this case. Now what about if the inputs were 0 or 1? So now Alice sees the same input. She has no idea what Bob's input is, so she must output the same thing. So she outputs a 0. But now what must Bob answer? Well, he's supposed to answer with a matching bit. B should be equal to A, so he must output 0. What about in the case where Alice has input 1 and Bob has input 0? Well, so now Bob has the same input as in this first row. And since he cannot see Alice's input, he must output the same as in this first row. So he must output 0. But now Alice is supposed to output a matching bit. So the only way she did not make an error already is if she output a 0. But now what about in the case 1, 1? Well, what must Alice output? Since in this scenario she output a 0 and she cannot tell the difference between this and these two cases because she can't see Bob's bit, she must still output a 0. What about Bob? Well, he cannot tell the difference between this scenario and that one because in both these cases he has input 1 and he cannot see Alice's input. So he must still output a 0. And so this is really the optimal strategy. That proves that the best they can do is 3/4 because we just force them every step of the way. Now, let's study this notion of local realism a little more carefully. So what's the most general situation that you can imagine? Well, the most general situation you can imagine is that, Alice and Bob are now these particles or these systems that we brought together for a little while. This is when quantumly we were supposed to have entangled them, but classically we are trying to come up with a theory which is local and real, it's realism. So these particles, when we brought them together, they communicated with each other and stored some information. Now, what could this information look like? Well, it could say, they could have talked to each other and they could have said, when we are far apart, experiments might be performed. So look, Alice, when you're far apart from me, if you encounter this experiment, react like this. So they come up with a list of all possible experiments and all possible responses to each of these experiments. They can also decide on probabilistic scenarios. So they can say, they can toss coins, and with some probability they decide to answer one way, and with some probability they decide to answer another way. So they can coordinate their choices. And so based on these coin tosses, they can decide today, because the coin tosses turn out to be all heads, we are going to answer in this particular way. But eventually, when they are far apart, they can no longer communicate with each other. So the only coordination comes from what they did when they were together. Okay, but now suppose in this scenario, they managed to beat the 3/4 bound. Can we say that this contradicts our proof from earlier? And the answer is yes. Because, you see, if they beat the 3/4 bound in this probabilistic scenario, then there must be some setting of the random bits, of the probabilistic choices, under which they beat 3/4. They do at least well as 3/4. Right? So if your expected outcome of an experiment is beats 3/4, then there must be some scenario in which you beat 3/4. Something must be over average, at least as big as average. And so fix those random bits. Fix that particular strategy for Alice and Bob. So pretend that that's what the random outcomes were when Alice and Bob met. Okay, fix those values once and for all. And now, when Alice and Bob are far apart, they manage to meet this CHSH condition that we wrote out, this particular condition, with probability greater than 3/4. And this contradicts our proof that no matter what they do, they cannot achieve this condition with probability better than 3/4. Okay, so this is the sense in which the CHSH inequality shows that nature cannot possibly be both local as well as following realism at the same time. So something has to give. And so the assumption is that locality still holds, but realism cannot. So the quantum state, the state of quantum systems, is really undetermined when you're not looking at them. It's only when you look at them that quantities such as what's the bit value and what's the sign, or what's the position of this particle, what's the momentum, actually emerge.